Okay, we want to graph y equals x minus 4 times x plus 1 times x plus 6. The zeros occur when any of these factors is 0. So we set x minus 4 equal to 0, and we get x equals 4. X plus 1 equals 0, we get x equals negative 1. X plus 6 equals 0, we get x equals negative 6. Side note, you don't want to just think it's going to be the reverse of this or the reverse of this or the reverse of x, because you might have some number in front of x. If this was 3x plus 6, then you wouldn't be able to do that. You'd have to set 3x plus 6 equal to 0 and solve it. So think, set this equal to 0 and solve it, set this equal to 0 and solve it, set this equal to 0 and solve it. Now, we look at end behavior, okay? Large X, large positive X implies a very large positive Y, so that the graph ends up ascending rapidly as you get out along the x-axis. And this is because if x is a very large positive number, it's going to be bigger than 4, so this is going to be positive. X is going to be big positive numbers, so x plus 1 and x plus 6 will also be big positive numbers. All of these will be big positive numbers, and when you multiply 3 big positive numbers together, you get a really, really big positive number. On the other side, a large negative x implies a large, very large negative value of y. Why is that? Because if x is a large negative number, it's going to be big enough to make all 3 of these negative, and when you multiply 3 large negatives together, you get a really large negative number. So you have this behavior on this side. So when we graph this function, we come up from here, we come through the axis, we come down here. We're going to have to turn around on the negative y-axis, come back up through 4, and that's kind of what our graph is going to look like. The y-intercept is going to be what? Negative 4 times 1 times 6 is negative 24. So just to put a scale on the y-axis, we'll label the y-intercept 0, negative 24. Now what we want to really talk about is how the number of turning points in the graph of the polynomial corresponds to the degree of the polynomial. So here we have a polynomial. What's the degree of this polynomial, and how many turning points do you see on the graph? Stop, think through that, fill in the blanks yourself, then pick it back up. Okay, you should have done that. Degree of the polynomial is what? Well, if we multiply these out, it's very clear we're going to have an x cubed. I mean, you know, if we take one term, if we take the x term from each of these factors and multiply them, we've got an x cubed. We're not going to get anything over a third power, so it should be very obvious to you why this is a third power. If it's not, use the distributive law, multiply it out, and prove it for yourself. The degree is 3. Number of turning points. Turning point, what do I mean by a turning point? Hopefully you know what that means, but it just means the graph is coming up and it turns around and goes back down. That's a turning point right there. And then it has a point where it goes from down to up. That's a turning point right there. Number of turning points is 2. Now it should be clear that if I put a bunch of other factors in here, I'm going to increase the degree of the polynomial. So if I've got 5 factors of this nature, I'm going to have 5 I'm going to have 5 factors, so I'm going to have a degree of 5. If all those factors are different, if none of them are repeated so that we would have a square of one of the factors, then we would have 5 distinct points on the x-axis, and the graph would have to pass through all of them. That would require the graph to turn 4 times. Okay? It's like you get the first 0. First time through the x-axis is kind of free, but if you want to get another one, you're going to have to turn around. Then if you want another one, you've got to turn around again. And if you got 2 more, you're going to have to turn around once, twice more before you take off for the outer realms. So, well, let's put it this way. Number of turning points is at most one less than the degree. Why is this? Well, the degree is going to be the number of linear factors you have here. The degree will be, well, you'll have at most 5 linear factors if you have degree 5, which means you'll have at most 5 zeros. If you have at most 5 zeros, you can't have more than 4 turning points. Okay, the turning points occur only in order to get through another 0. So we have this. Whether you understand why that's so or not, it's so you kind of want to remember that. The number of turning points can be less than this, okay? If you have degree 5, you don't necessarily have 4 turning points. For example, you could get degree 5 by multiplying this by a quadratic that has no zeros. A quadratic whose graph remains either totally above or totally below the x-axis. And you wouldn't get any more turning points because you still only have 3 zeros. So it's possible to get like a degree 5 polynomial with only 3 zeros. So I'm going to say that the number of turning points can be even less because we can have quadratic factors that can't be 0. Okay? That's not true of linear factors. If it's a linear function, it's going to have a 0. Quadratic factors, though, could have zeros. You could have quadratic factors that have 2 zeros or 1 0. But if you have quadratic factors that have 2 zeros, then you're always adding 2 to the number of zeros, and that's going to give you more turning points. That's a subtlety that you don't necessarily have to completely understand, but you're better off if you do.